Let me talk about this Bayesian multiple regression. The first step is to specify the model. So here we have a commonly seen the structural component, the structural model for multiple regression, right? We have a continuous response variable y, and then it is equal to x beta plus epsilon. X is, could be could contain array of variables. And sometimes we can call them predictors or covariates, right? Beta are, slopes or parameters we attempt to estimate. Then we have this error term, epsilon, without loss of generality, we can assume this error term follows a normal distribution with mean of 0, and that's a very common assumption. And variance is equal to sigma square, and this is identity matrix. Okay, basically it says, well, for every single error term, right? Because we have n observations, then we have n error term, and all these error terms follow the same distribution, okay, with the same standard deviation there. Equivalently, I can assume that the conditional y, that is y conditioning on covariance x and parameters beta, follow a normal distribution, but in overwhelming majority of the cases, usually people talk about this error term, that is epsilon. Epsilon follows a normal distribution, the equivalent of saying this conditional y follows a normal distribution. And then what we need to do is to construct this likelihood function, right? For the likelihood, the data is given, then we want to estimate the parameters, which are beta, parameter vector, right? And sigma square, okay? And if you recall, in one of our previous slides, I have exact same equation for the likelihood. The only thing that differs between these two is that in this case, I use matrix language to express this likelihood as opposed to, the scalars that I use, right? In which we only have a single covariate, right? Okay. Next step is to specify priors, right? In this case, I'm going to show you that the normal prior for beta turns out to be the conjugate prior. I always say conjugate prior, that is, basically, if we supply a prior conjugate prior refers to prior that after being multiplied by likelihood is going to become a posterior prior that comes from the same family as does the prior, okay, provided at the very beginning, or exactly the same prior, with different parameters, okay? Then we say this prior is conjugate to the likelihood, okay? And in this case, what we're going to assume is that the sigma square is fixed. So this is a kind of, conditional prior for beta. So with sigma square fixed, we can focus on this term and this term. So in Bayesian estimation analysis, any constant that does not involve parameters to be estimated can be dropped because those terms only serve as proportionality terms, and they don't affect the derivation and simulation of the posterior. Okay, so there are like auxiliary numbers there. They don't play essential role in the derivation. Okay, the next step I want to do is to expand this matrix multiplication. If you're not that comfortable with matrix multiplication, you can watch my lectures about matrix. So it becomes y prime y minus y prime x beta. So prime here refers to transpose. So y prime refers to y transpose minus beta prime x prime y and plus beta prime x beta. Again, we can drop y prime y. Why? I'll let you think for 3 seconds. Well, again, is because y prime y does not involve the parameter vector beta. Okay, parameter vector beta. Okay, and people say, what about this sigma square? It stands alone. Well, when I say, well, does not involve, it also includes multiplication. In this case, sigma square here actually is going to multiply with beta, right? But for y prime y, after multiplication, again, it does not involve beta. No. Remember that here we assume sigma square is what? Is a constant. Okay, so this term, after we combine this term, it's going to become this term. Okay, then here's the trick. We're going to multiply both the denominator and the numerator, both by x prime x inverse. Then we have this term. With some, here I want to say, well, simple, but really not simple, matrix rearrangement. We can compare this expression to a normal expression for normal density, right? It's not that hard to figure out that for this term, okay, for a variable follows this probability density function or has this probability density function, it's not that hard to find out that it has a variance of this and mean equal to x prime x inverse and x prime y. Okay, x prime y. So the posterior again. So this is a posterior. Okay, it's a posterior for beta. Note that this is conditional on sigma square. Okay, it's also a normal. Begins with a normal. It goes through a normal likelihood. Turns out to be a normal. Okay, so this is a conditional conjugate prior for beta.